Good morning, everyone. Today we are going to learn the structures and properties of ceramics, and this is part three of this topic. And we have covered use the two sessions to cover this topic. And today we are going to continue our talk. And here are today's objectives. First, we want to learn the defects in ceramics, and we learn the defects in metals and also metal alloys. And now we want to learn the defects in ceramics, and we want to learn the phase diagrams of ceramics also, and we want to learn mechanical properties. After we know these is microstructure things, and they want to know what kind of mechanical properties the ceramics have. And first, and as we learned the defects about the metal and metal alloys, and we also talk about the point defects in ceramics. First, we have vacancies. Right? Vacancies exist in ceramics for both cast irons and irons. And the difference between the ceramics material and this metal material is that for ceramics we have uh, typically we have two uh, kinds of items. One is called cast irons and one is irons. But for metal, we have only one item, one kind of items. And we have vacancies. Okay, so this you can see this vacancy cast iron vacancy here. That means this cast iron supposed to be here, but so for some reason this cast iron is missing. And also similarly, we should have a iron here, but for some reason this iron is missing. The big circle is missing. So this is called the iron vacancy, and this is cast iron vacancy. And interstitials. And interstitial means that something extra and stays uh, something extra and stays in between the items. For here, cast iron interstitial, and we have our one cast iron already, but we have extra one. So this extra one is called cast iron interstitial. Interstitials exist for cast irons. Interstitial are not normally observed for irons because irons are larger relative to the interstitial size. Right? So this is you should know that. You can see these bigger circles and bigger spheres, and they stand for this irons, and small circles, small spheres. They stand for these cast irons. And be very very careful about this. Any questions regarding this slide? No question. And we talk about Frankel defect and this Schottky defect. Frankel defect, a cast iron vacancy and cast iron interstitial pair. So there is a cast iron vacancy and a cast iron interstitial, and both of them exist. And for example, this is a Frankel defect. Frankel defect here. Cast iron vacancy and this cast iron vacancy and cast iron interstitial. Cast iron interstitial comes here. But supposedly this guy should stay here, but for some reason, and one of these guy, it does that without loss of generality. We can just assume either one. Okay, either one will be okay. Either one of these cast irons just moved from this position to this position. Now you can see because this guy moves from here, so here has nothing. This empty. This will be a cast iron. This vacancy, and because this guy moves to the new location, and so this one is also called cast iron interstitial. So that means one single cast iron moves from one location to another, and so the original location becomes vacancy, and the new location has they have additional cast iron here. So this is called cast iron vacancy and cast iron this interstitial pair. Both have both. And Shockley defect. So Shockley defect a paired set of cast iron and iron vacancies. cation and iron matrices for this one. So supposedly here I should have this is iron, a bigger sphere or bigger circle, and here should have a smaller one, cation. But for some reason, this guy disappears and this guy disappears. All right. So here is the equilibrium concentration of defect, and we use this equation to calculate the equilibrium concentration of this is this Frankel, the Frankel defect. This will call the Shockley defect. We use this equation, and T is the absolute temperature, and the unit is Kelvin, Kelvin degree. Any questions regarding this slide? No question. So then we can imperfections in ceramics and electroneutrality, right? So this charge balance must be maintained when impurities are present. And I told you guys many times the electroneutrality is very important. Why? Because if this material is not in the state of electroneutrality, and so this material has a tendency to have chemical reaction with the neighboring materials, and which means that this guy is not in a state of equilibrium, not in a stable state. We should avoid these kind of things. And so, for example, this is a sodium chloride. We have a sodium cation with the chlorine, and this iron, and substitutional cation impurity. So here, okay, so here, and so this is calcium, and if we have calcium, one calcium, right, one calcium cation, and it can substitute two sodium this cation, because sodium cation has only one charge, but calcium it has two. So this is without purity. So this is a calcium cation purity, and so here is a cation vacancy, okay? Because we have a cation 2+ here. So this one guy carries two charges, and so this is impurity. So you can see to maintain electroneutrality, so this one of the cation needs to be removed. Original cation needs to be removed. Any questions regarding this slide? Okay, so the substitutional iron impurity, and for the same thing, this is the sodium chloride, and now this time we have oxygen cation. So this oxygen cation carries two negative charges here. So that means one oxygen cation can substitute two chlorine iron. Iron, oxygen iron can substitute two chlorine ions, and so that means, and you can see here, we need to delete one chlorine iron in order to maintain electroneutrality. So this is very important, guys. Any questions regarding this slide? Okay, then we take a look at this one. So this one, see imperfections in ceramics. Now this time, we have Fe3+, Fe2+, and so this is Fe iron. This is iron cation, iron cation. These two guys have different charges, and both of these two ions, they are iron ions. So this is oxygen ion. And so here we have Fe2+ vacancy here. Fe2+ vacancy, right? So here we have a vacancy here. And so this 1, 2, 3. So this is a 3. So here is a 2, because this is a vacancy here. And then you can see imperfections in ceramics. So this interstitial impurity ion item. So this is substitutional impurity ion, so you substitutional, and so this is kind of have a very comparable radius with this is the original. This is ion. So this is a substitutional. This is interstitial impurity atom. And then we talk about diffusion in ionic materials. And in order to diffusion exists not just in the metals and metal alloys, but also in these ionic materials, means ceramics. In order to maintain charge neutrality in an ionic material, an ion vacancies occur in pairs. Ion, cation and ion. Vacancy, if one is missing, another one needs to be deleted as well. And they form in non-stoichiometry compounds. Non-stoichiometry means what? Stoichiometry means that the number of one material and another material, and they are closely following the chemical formula. And the non-stoichiometry means that, and so for some reason, this material, the number of these atoms and ions and a number of that ions, and they are not following the chemical formulas. So this kind of state is called non-stoichiometry. And they are created by substitutional impurity ions and having different charge states than the host ions. In any event associated with the diffusive motion of a single ion is a transference of electrical charge. In order to maintain localized charge neutrality in the vicinity of this moving ion, another species having an equal and but opposite charge must accompany the ion's diffusive motion. So possible charged species include another vacancy, an impurity atom, or an electronic carrier, for example, a free electron or hole. So these observations need to be understood clearly, and so you can make the correct judgment whenever I give you some problems to solve. Any questions regarding this slide? So one important thing is that the material, either globally or in the vicinity of that ion's impurities, the electroneutrality must be maintained. Otherwise, this material is not in a stable state. It has tendency to have chemical reactions with other neighboring materials, which is not what we wanted. And then we talk about ceramic phase diagrams. And when we talk about phase diagrams for metals and metal alloys, and here is ceramic phase diagrams. And also, what is a phase diagram? And so here is temperature. The ordinate is temperature. Abscissor is this is the composition of some material. And for here, okay, so we have two compounds. This is a chromium oxide along with this is aluminum oxide, this diagram. So this is the position, means the 0% of the chromium oxide. That means 100% of aluminum oxide. And so this line stands for that the state that we have 100% of chromium oxide. That means 0% of sodium, aluminum oxide. So we also have, and this is the two curves. One is liquidus, one is a solidus curve. So this is liquid, right? If the temperature is high, okay, from this is 0% to 100% of chromium oxide. When the temperature is high enough, and we have liquid, single phase liquid. And then if we lower the temperature, and we can get two phases that consists of both liquid phase and this is a solid phase. If we further lower the temperature, and when this is the line intersects, and so this is a solid curve, and we will have solid phase only, right? So this is a solid phase. This solid phase actually is the aluminum oxide and this chromium oxide. This is solid the solution. This is a solid solution. Be very careful. This is solid solution. Any questions regarding this phase diagram? And this is isomorphous and phase diagram. And another example is a magnesium oxide and aluminum oxide diagram. So here is magnesium oxide. So this is 100% of aluminum oxide. This is 100% of magnesium oxide, but 0% of aluminum oxide. And so this phase diagram is much more complicated. And so here is we have magnesium oxide solid solution. SS means solid solution. So here is magnesium oxide solid solution plus the liquid. Right? So here is the two phases, and here is the liquid phase, and here is magnesium oxide solid solution along with magnesium aluminum oxide solid solution, solid solution here. And so here this is the liquid, the phase, solid phase plus liquid. So there is another magnesium aluminum oxide solid solution plus oxide aluminum oxide. So this one is much more complicated than the previous one and we just talked about. And the same thing, given any combination of this aluminum oxide at then with lower temperature, and we can see the phase changes from one state to another, and how it changes, it depends upon the combination of aluminum oxide. So based on the combination, okay? So you can see for different vertical line and different paths, have different paths, and then we can get different phases. Any questions regarding this slide? No question? Then we talk about zirconium oxide and this calcium oxide diagram. Is they are more complicated. They are more complicated. I just show you guys. And three crystal structures we have, and tetragonal, monoclinic, and cubic. So this is more complicated. This is still liquid, okay? So this liquid is another liquid and cubic plus liquid plus and calcium zirconium oxide. And so this is you can see this is a tetragonal zirconium oxide solid solution. So this is cubic plus tetragonal in this area. So this is a cubic zirconium oxide solid solution. And so here is a monoclinic plus calcium zirconium oxide. It's very complicated. And here is a line, is a compound line. And so here is another area. And you can see this one is much more complicated, right? Because you can see how many elements we have here, how many ions we have, how many kinds of ions we have, zirconium oxide and calcium. Be very careful, guys. I just show you this phase diagram, so you know how to interpret this phase diagram, especially if I give you this not necessarily this one, any kind of phase diagram about ceramics, and then give you the combination, and then you ask you to use your own language to tell me when you lower the temperature and how the phase changes, and you should be able to tell me. Okay, so this is one of the learning objective of this class. Questions so far? No question? We'll move on to the next one. So this is silicon oxide and this is aluminum oxide diagram. And so here is 0, 100, and you can see these two guys, they can solve each other from 0% to 100%. This liquid and crystalline, crystalline, moonlight, this moonlight, crystalline, alumina, moonlight, and this liquid alumina. So you can see different temperatures. Another characteristic of these phase diagrams is that you can see the melting temperatures for all of these ceramics are very, very high, much, much higher than those for the metal and metal alloys. I hope you have noticed that this is the huge difference. Any questions so far? Now, up to now, we have talked about this is uh, impurities and defects, impurities in the ceramics, and then we talk about the several typical phase diagrams of some uh, ceramics, and then we are going to talk about how these impurities and this is the defects and phase diagram and of influence these mechanical properties. Mechanical properties. So this here, ceramic materials are more brittle than metal. Why is this so? Why is this so? So hardness is measured using Vickers and Knoop these techniques. And you should remember that we have 4 different kinds of hardness testing techniques. One is Brinell, and one is Rockwell. And we have learned this Rockwell hardness testing in our mechanical engineering lab. If you have taken this lab or you are taking this lab concurrently, and you should already have learned on how to use Rockwell hardness tester to hardness test the materials. Right? And so then Vickers and Knoop techniques, these two hardness testing techniques, they are for micro hardness testing. And for this is the ceramics. Right? This is for ceramics. We need to use Vickers and Knoop techniques. Why? Because and Rockwell hardness testing along with Brinell hardness testing, and they are mainly for metal and metal alloys. Um, because metal and metal alloys, and they are more ductile, and if we use the bigger indenter and to compress the samples, we will not have cracks. Okay? But for the brittle material, for example, ceramics, if we use a so huge indenter to compress the sample in order to get the hardness, and we might induce the cracks, which is bad. Questions? No question? And we talk about, we consider mechanism of deformation. In crystalline is a dislocation motion. This is the mechanism of deformation. In highly ionic solids, dislocation motion is difficult because in this case we have fewer slip systems, resistance to motion of ions of like charge. For example, ions pass one another. In highly covalent solids, slip is difficult and brittle, and the covalent bonds are relatively strong, and limited numbers of slip systems, and dislocation structures are complex. Questions regarding this slide? And then we talk about the next slide. So for this ceramics, and how can we do the mechanical testing? And we use how to measure the elastic modulus. And we know that also in the mechanical engineering lab, and we usually teach students how to do the tensile testing for 3 different materials. One is the steel, one is the ceramic, steel, one is the cast iron, another one is aluminum. But for these brittle materials, and we cannot use tensile testing machine because it is very brittle. Brittle materials and the ultimate strength for compression is much higher than the ultimate strength for tensile testing. So that's the reason we cannot use tensile testing to measure the elastic modulus, and then we need to have alternative. And then we usually use 3-point bending testing to do it. This fractal testing. So here is a sample. So here is a supporter. Here is a supporter, and we have the external force in the middle, and then the tensile testing, and then this cross-sectional area. Okay, cross-sectional area can be rectangular, can be circle, and then this deflection is a midpoint deflection, and we measure the relationship between measure the midpoint deflection when we change this f, and then we will have we can generate the curve between f and this delta. Determine elastic modulus according this is the diagram. This is the force, applied force. So this is the corresponding, the resultant deflection, midpoint deflection. The slope is the Young's modulus. The slope, I mean, it is the slope equals f divided by delta. This is the slope f divided by delta. For Young's modulus, and we have these equations to calculate. Right? So this equation is for cross-sectional area, rectangular cross-sectional area. So this equation is for circular cross-sectional area. Any questions regarding this fractal testing for these brittle materials? No question. We move on to the next one. And this is a strength, measurement of fractal strength. Previous slide talks about how to use fractal testing and to measure the Young's modulus. Now here is the stress here. So this F, so this is the location of maximum tension here. So delta, midpoint deflection. So fractal testing, right? So it's fractal testing strength, that's the material parameter. It equals these two equations. Also, these two equations are for different cross-sectional areas. This is rectangular, this is circular. And so F is the force at which so this material starts fracturing, starts cracking. So this is called FF. So for typical material, silicon nitride, silicon carbide, aluminum oxide, glass, this is soda lime, and we have this sigma fs fractal strength here, and also corresponding Young's modulus. Any questions? Any questions regarding this slide? And you might ask me how this slide is different from the previous slide. And I need to tell you, previous slide is used to measure the Young's modulus. So this one is used for measuring the fractal strength. Okay, so for that one, you don't need to apply the load until these sample fractures. But for this one, you need to keep increasing F until the material fractures at this point. So this is the difference between these two slides. Any questions so far? No question? No question. Move on to the next one. And then we talk about the influence of porosity. We know the ceramics, they are different with the metal material. They might have some a porosity there. These have pores here. How big the pores are, how this is the porosity influence the mechanical property. And so here, this equation, this empirical equation, Young's modulus, and this E0, and so this is P porosity, right? And P is a volume fraction porosity. You can see from 0 to 100, 1.0, 100%. And you can see modulus is decreasing substantially. So this is the best fit curve. So this is 5 points, they are experimental points. So this is how people get this equation, best fitting. You can best fit these 5 points in order to get the best fitting curve. Any questions? No question? No question. We move on to the next slide. So you can see the sigma. Okay, so this is sigma fs. Also, it is substantially influenced by the porosity. You can see it goes down very, very quickly. As again, these tiny circles stand for the experimental data. So this curve is the best fitting curve. Summary for today's lecture. First, interatomic bonding in ceramics is ionic and or covalent. And ceramic crystal structures are based upon maintaining charge neutrality, electron neutrality. This is very, very important. Cation and iron radii ratios. And you can see how different, how this radii ratio affects the defects and also impurities there. Imperfections include atomic point, vacancy, interstitial cation, Frankel, Schottky, and impurities, substitutional, interstitial, maintenance of charge neutrality. So that is the basic line, and to determine the position, also the number of impurities, the room temperature mechanical behavior, and we use fractal testing, and this is for linear elastic measurement of elastic modulus, brittle fracture measurement of fractal modulus. So this fractal the strength. Any questions so far? Without any questions, and I'm going to end today's session. I need to tell you guys you need to review these materials, and also if you have any questions, feel free to come to my office or just email me, and so we can discuss. Thank you very much for your attention. You have a nice day.